What if time isn't what we think it is? We live by the clock's relentless rhythm. We wake up at 7, rush through meetings by noon, and collapse into bed by night. Time defines our very existence. We're born, we age, we die. We remember the past, act in the present, and dream about the future. Time feels like the ultimate constant, an unstoppable, forward-moving force shaping everything we do. But physics? Physics suggests time might be the greatest illusion of all. Let's start with Einstein. His theory of relativity changed everything. Before him, time was thought to be absolute. A universal tick-tock experienced the same everywhere. But relativity revealed something mind-bending. Time is not a standalone force. It's fused with space into a single, malleable entity called space-time. In this four-dimensional fabric, your past, present, and future are not fleeting events. They're fixed coordinates. Just as all the locations on a map exist at once, so do all points in time. Imagine a film reel. Each frame already exists, but you experience the story one scene at a time. This idea forms the basis of the block universe, a reality where time doesn't flow. It's all there, static. You don't move through time. Instead, you are a still thread in a vast cosmic tapestry, your life etched immutably across space-time. So why do we feel like we're moving? Why do we remember yesterday but not tomorrow? Why do we age forward, not backward? Why does a shattered glass never unshatter? The answer lies in entropy. Entropy is a measure of disorder in a system. The second law of thermodynamics tells us entropy always increases in a closed system. In simpler terms, the universe moves from order to chaos. Hot coffee cools down. Ice melts. Buildings decay. These aren't just unfortunate realities of life, they're markers of the arrow of time. Entropy provides time with its apparent direction, from low disorder to high. But here's the paradox. The fundamental laws of physics don't care about direction. Newton's laws, Maxwell's equations, and even the Schrödinger equation work just as well in reverse. You could mathematically rewind a universe, and the equations wouldn't blink. So why can't we? Some physicists argue the answer lies at the beginning, the Big Bang. The early universe was a state of incredibly low entropy, a cosmic egg of perfect order. From that singular, improbable beginning, disorder has grown, like a deck of cards being shuffled more and more chaotically over time. The flow of time, then, is not a fundamental feature of the universe. It's a side effect, a statistical bias caused by our ordered origin. If this journey through the illusion of time sparked your curiosity, consider hitting that like button. It helps this content reach more curious minds like yours. And if you're fascinated by the mysteries of the universe, subscribe and tap the bell icon so you never miss a moment, real or imagined. Now, quantum physics adds another layer of weirdness. In the quantum realm, particles don't follow neat trajectories. Instead, they exist in a haze of possibilities, a superposition of multiple states. A particle is here and there, spinning this way and that until observed. Observation collapses this cloud of probabilities into a single outcome. This raises a wild question. Does reality, including time, only exist when we observe it? And if so, could our observation not just affect the present, but also ripple into the past? In fact, some quantum experiments suggest this might be true. In delayed choice quantum eraser experiments, decisions made after a particle has chosen its path can seemingly affect its past behavior. It's as if the future reaches back in time and changes history. Cause and effect get fuzzy. Einstein's own equations don't forbid time travel either. In general relativity, there are solutions called closed time-like curves, essentially loops in space-time. If such loops exist, then time is not just a one-way street. You could, in theory, revisit moments, or even meet your younger self. These remain theoretical, of course, and would likely require wormholes or exotic matter to exist, but they are mathematically possible. Now let's take this one step further, into the mind of physicist Julian Barbour. Barbour argues that time doesn't exist at all. According to him, the universe is made of countless nows, individual frozen snapshots of the universe. There is no motion, no flow, no past or future. Only static configurations. Our perception of time, he says, is like flipping through the pages of a photo album. It feels continuous, but it's an illusion created by memory and consciousness. If Barbour is right, then everything, every heartbreak, every kiss, every sunrise is just one still frame in an eternal mosaic. Our sense of a life story? Just our mind connecting these frames into a narrative. This view aligns with some quantum interpretations, especially those that emphasize the observer's role in collapsing reality into definite states. Could it be that time itself is born from consciousness? That each mind spins its own timeline from a timeless field of possibility? It might explain why time seems to bend around our emotions. A minute in terror feels endless. A day in joy flashes by. When we meditate deeply, time can seem to slow or vanish entirely. Psychedelic experiences or near-death moments often strip away the illusion of time, revealing a sense of infinite presence. Could these altered states offer a glimpse into the true timeless nature of reality? Not everyone agrees time is an illusion. Some physicists insist it must be real to make sense of causality and quantum decoherence. Others turn to string theory, which posits extra dimensions of space and potentially time. In these higher dimensions, time might not be linear. It could branch like a tree, split like light through a prism, or form loops and intersections we can't yet imagine. These aren't just science fiction plots. They're backed by serious mathematics. String theory and loop quantum gravity both hint that time might emerge from something more fundamental, something not yet understood. And the implications are staggering. If the block universe is correct, then free will might be an illusion. Your birth, your biggest choices, even your death, all already there, unchanging, etched into the fabric of space-time. But if time is flexible and observer-dependent, as quantum theory suggests, then maybe we do influence reality not just ahead, but in all directions. Could we one day learn to navigate this temporal landscape? Quantum computing, with its ability to tap into superpositions and entanglement, might offer a tool to glimpse, or even manipulate different timelines. But for now, these remain tantalizing questions, just out of reach. Even philosophers are divided. Plato imagined time as a moving image of eternity. Augustine said he knew what time was until someone asked him to explain it. And today, as physics peels back the layers of the universe, time seems less and less like a ticking clock and more like a human invention, a practical tool for survival, but not a fundamental truth. If entropy is what gives time its arrow, then the universe may end not with a bang, but a whimper. A heat death of maximum entropy, where no work can be done, no life can exist. But if time is an illusion, then perhaps the end never really comes. Every moment, from the first spark to the final flicker, simply exists forever. So what is time? A river that flows, a fabric that bends, a loop that repeats, or a mirage conjured by our minds? Physics has no final answer, and maybe that's the beauty of it. The clock ticks, yes, perhaps only because we're listening.